Alright, good morning, good afternoon, good evening, class, whatever time you happen to be watching this. Today we went over limit laws, so this is part of section 2.3. We're going to take this slow, probably go over this section over the next 3 days. So I guess, well, next 2 days, I guess, because today we already went over this one. Okay, so limit laws are very similar to a lot of laws we have discussed in previous topics. Okay. But the following, before we can apply any of the limit laws, then the following must exist. First, the limit of f of x as x goes to a and the limit of g of x as x goes to a must exist. Okay? And if this is true, if both these limits exist, a lot of cool things happen. Okay, first is that limits can be added together. So if the limits exist, then we can say the following. The limit as x goes to a of f of x plus g of x is exactly the same as the limit as x goes to a of f of x plus the limit as x goes to a of g of x. Okay? And we'll illustrate that with this function. So here's a function. This is g of x. Let's say this is g of x. And this is f of x. And if the limit exists, so let's say I have to excuse my penmanship. I don't actually have a pen, so I'm doing this with a mouse. Limit as whoops. Let's change that to not a, like an actual number. So let's say 1 of the function f of x plus g of x. Okay, well, this is going to be the same as, if I were to say the limit as x goes to 1 of f of x plus the limit as x goes to 1 of g of x. Now this is true as long as the limit of f of x exists and the limit of g of x exists. So let's look at x equals 1, which is here. Here is x equals 1. Okay, as we can see, for f of x, the limit does indeed exist because the left side and the right side both approach the same number. In this case, it's going to be 1. So this is change. So this whole thing is 1. Okay. Now g of x, same thing. Approaching from the left side goes to a particular number, approaching from the right side goes to a particular number, and that happens to be 0. So altogether, this is the limit of those two functions is equal to 1. Okay. Now to illustrate this even further, I'm going to go and bring up this graph. There's Desmos. Let's fire up Desmos. I think I have it. There it is. There's my piecewise function. Okay. There you go. There's my piecewise function. Now, if I plot h of x as f of x plus g of x, let me just change the color. It's a little easier to differentiate. There we go. Done. And I guess I'll hide the other functions. There you go. So there's this is f of x plus g of x. Okay. And then here for reference, there's f of x, there's g of x, h of x. So as the sum of the two functions approaches, as x approaches 1, the sum of the two functions approaches this particular number here. From the left side, it's approaching, looks like 1. And from the right side, it's doing the exact same thing. It's approaching 1. There you go. So the graph shows us that if I add the two functions together, the limit as x goes to 1 of the sum of the functions is really the same as the sum, as the sum of the limit of f of x and g of x. Okay. Yeah. So that's how we illustrate the that rule. Right. Next. So, if the sum is true, then the limit is also true, or the difference of limits is also true. So sum of limits, and it goes hand in hand, but the difference of limits also exists. So if I have the limit of f of x minus g of x, then that is the same as saying the limit of f of x as x goes to a minus the limit of g of x as x goes to a. Okay. Oops. All right. So, and we'll illustrate again from here. So if I have, let's say, g of x is the green line, and let's make the limit as x goes to 1 of f of x minus g of x. This is going to be the same as the limit as x goes to 1 of f of x minus the limit as x goes to 1 of g of x. Okay. And in this case, we can do the same thing. Going to from the left is 1, from the right is 1, so this is 1 minus 0 is going to be equal to 1. And we'll show that again with my graph. So let's take a look at, where is it? There it is. So there's h of x. Let's change it to h of x minus g of x. And as you can see, this difference of functions, as I move closer and closer to x equals 1, the value of the function gets closer and closer to 1. Same thing on the other side. Exact same thing. There you go. So the limit is going to be 1. All right. Now, next, this one, limit multiplied by a constant. Let us look at a graph of f of x. Okay, so here's f of x. If I consider the limit of f of x as x goes to 1, I can see that the limit is equal to 1. Now what if I change f of x to, say, 3 times f of x? As follows. Well, what goes from our function transformations, if I multiply f of x by 3, the function gets vertically stretched by a factor of 3. And what does that do to my limits? Well, let's take a look. As x goes to 1 on h of x, it looks like the value approaches 3. So lo and behold, the limit gets multiplied by 3. This is our next rule. Our next rule then is, if I take the limit as x goes to a of a vertically transformed function like c times f of x, then the limit is really just c times the limit of the original function as x goes to a. Okay. And we've illustrated that with my vertically transformed graph, and I'll show that again. So as x goes to 1 for the original function, the function goes towards 1. If I multiply that function by 3, the limit is now 3. Okay? So multiplying by a constant, you just multiply the limit by that same constant, and you've got your limit. Now what if you multiply by a function? Well, so this is where we get our product of limits. Product of limits is, as you would expect, if you take the limit as x goes to a of f of x times g of x, this is the same as saying the limit as x goes to a of f of x times the limit as x goes to a of g of x. Okay? And we can see that again. So let's go back to my graph. And so f of x times g of x. We'll hide this. And there you go. So there's my graph. And I'll throw this up there. Okay? So let's say I want to calculate the limit as x goes to 1 of f of x times g of x. Okay. Well, according to our function, the red line, as I get closer and closer to x, it looks like I'm getting closer and closer to 0. Okay. And if I were to look back here and actually calculate it according to this rule, well, the limit, so very familiar to us now, the limit as x goes to 1 of f of x times the limit as x goes to 1 of g of x, well, this is just 1. This is 0. 1 times 0 is equal to 0. Okay? And on the actual, when we graph the actual product of the functions, it is true. We end up getting 0, like that. Alright, so product of limits, you just multiply the limits together. We'll actually build on this definition a little bit tomorrow. We can actually expand the product of limits to give us a new rule. Okay, but that's for tomorrow. Alright, and lastly, we'll talk about the quotient of limits, because if we can multiply limits, then we can do the exact same thing with division. So, if I have the limit as x goes to a of f of x divided by g of x, then it is true that we can say the limit as x goes to a of f of x divided by the limit as x goes to a of g of x. There's one other condition, though. And that is the limit of g of x, in addition to existing, the limit of g of x cannot equal 0. Otherwise, bad stuff happens. Okay. So, let's give it a graph. Let's give it a graph. G of x. Take that out. There we go. There we go. Now notice in this particular function, so the division of f of x and g of x, we have an asymptote at x equals 1. Why is that? Well, let's take a look at g of x. There's g of x. What happens at x equals 1? G of x is at 0. So when that happens, then we have a vertical asymptote on the division of the functions. Okay. Other than that, though, all the other values are perfectly fine. Like, for example, let's say let's calculate the limit. Okay, so let's calculate the limit as x goes to, let's say, 2. Because I can't pick 1 anymore because bad stuff happens. F of x divided by g of x. Okay, well, this is the same as the limit as x goes to 2 of f of x divided by the limit as x goes to 2 of g of x. Okay. On the function here, on the actual graph of the division of the function, it looks like it's going towards 1. Sorry, 1. It's going towards 1. As x goes to 2, the function moves towards 1 on either side. Okay. And the rule should mimic that. So, as x goes to 2 for f of x, remember the black line is f of x, it's going towards 1. This will be 1. Divided by, and as g of x goes towards 2, it's also going towards 1. 1 divided by 1 is equal to 1. And that matches up perfectly with what we are doing on the actual graph of the quotient of the two functions. So this is, as x goes to 2, the quotient of the function goes towards 1. And it's true for either side. So that limit exists. X equals 1 gives us problems, so there's no actual limit. Now, as one student pointed out earlier, if you consider at x equals 1, there is a left side limit. Left side limit as x goes to 1 is negative infinity, and the right side limit as x goes to 1 is positive infinity. If they went the same direction, so if both the left side and right side both went to negative infinity, you could say that the limit's negative infinity. And similarly, if both the left side and right side went to positive infinity, you could say the limit is positive infinity. But since they don't go in the same direction, x equals 1 has no actual limit. Okay. Alright, so that's what we did today. Tomorrow we're going to talk about more rules, which will build off of these 5 basic rules. Okay. Assignment is on the blog as well as here. Pick any 3 in those. Pick any 3 from 3 to 9. Alright, good luck, and if you have any questions, come see me in class.